Good afternoon, everyone. Let's get started. So last time we were talking about our approaches to open domain questions, answering all sorts of questions where the source of information for that question is not given to the system, rather the system needs to both retrieve it and then answer the question in the context of the retrieved document. And last time we were focusing on this retrieval part where we have some kind of collection of documents from which we need to, for a given query, find out which documents are relevant and which are not. We talked about a classical information retrieval approach using BM25, which is a fancier version of TF-IDF. And then we talked about the dense retrieval, where we encode documents in a query with the dense representation and then use cosine similarity or dot products to determine the importance. Now, there are a few more things to mention about the retrieval. First thing I want to mention is that the way we were talking about the retrieval at the end of the last lecture, where we have all these vectors, where all the documents become, each one of them becomes a vector and a query is a vector, and we do dot products between a query vector and each of the document vector. That's a problem, an instance of the problem called maximum inner product search. And obviously there is a linear time implementation, but it's generally too slow to use in practical settings. So to kind of speed up this mixed problem, the common choice is to use the approximate nearest neighbor algorithm. So instead of searching over the entire data store, which is now a data store of vectors, you are maybe doing some either pre-clustering and then you're searching within the most relevant cluster, or you are quantizing your vectors. You're doing something that won't give you necessarily the exact result that the full mix would, but it's necessary for practical settings. And this brings me to FICE. So first I want to say that when I talk about classical information retrieval with BM25, I mentioned that we need an index, which was just a data structure where we had for every token, we have information about which documents this token appears in. And now when we switch to dense retrieval, the idea of what the index is has changed a little bit. Now, the index is referring to this collection of these vectors. And you need to find which vector is a most suitable one. But you want to create a representation of this data store, which will enable to find the most similar vector fast. And then this becomes index when you have a little bit fancier representation of your data store vectors. And FICE, developed by Facebook AI's research group, they have developed this library, which is very, very commonly used to produce an index for your collection of your data store vectors. We won't go into detail about how it works, but it builds an index by dividing this space of our data store vector using some clustering techniques. And at the search time, instead of searching over, every single data store vector, we are looking at the most relevant clusters vectors. So if you, end up using a dense retrieval, most likely you will also use FICE. Yeah. Okay, another thing we need to talk about is how do we evaluate retrieval? All right, like we had decided, okay, I'm going to use dense retrieval or whatever, and I'm going to train it. For the training, I need some data. We said we need a query tied with a positive relevant document and a collection of irrelevant document that usually comes from whatever some poorer version of retrieval things are relevant documents. And given this training data, we are going to train the dense retrieval using the approach I have covered at the end of the last lecture. So we have seen that loss function I have shown you last time, and then we calculate the loss, back propagate through both versions of BERT, right? The one which encodes queries and one which encodes documents, and we have trained, and now we are done. And at the test time, we need to do basically the searching in our index. But how do we evaluate whether this whole system we have built in this way is good or not? We are going to use as one of the metric choices, and we won't talk in this course about other ones, but you can choose your standard precision recall F1, where the precision and recall notion is slightly different than in classification. Basically, you retrieve some documents, right? But in your test data, you actually know which documents are relevant or not. So you can see amongst those that your system has retrieved, how many of them are actually relevant, and that would be precision, right? However, it wouldn't be so nice that my system is very precise, but it doesn't really retrieve most of the relevant documents. So we also want to check out of those that are truly relevant in our test data annotations, how many have I actually retrieved, right? So if I had 3 relevant documents annotated by some person, and I have retrieved only 1, and that one is truly relevant, my precision here is amazing, so it's 100%. But if since I didn't retrieve 2 out of 3 documents, my recall would be really poor here, only 30%, 33%. So we will, as always, use F1 to kind of combine these 2 important measurements. The issue with this metric is that it doesn't really measure the performance of a system where ranking is important, right? So right now we're just talking about retrieve top 3 documents, but I'm not really interested in whether the order in which I give these documents. And typically in retrieval applications today we are not, because we are going to retrieve top something and we are going to place them into our context, and we won't do anything special with the order. Although I'll come back to, when you might consider the order when you're crafting the input. So one way to evaluate a retrieval, the one I'm teaching you about, is to use F1 measure, but keep in mind that this doesn't evaluate whether you have given the right ranking of the documents. Okay, I want to finish with this slide for the retrieval, which is referencing this amazing tutorial from ACL 2023. ACL is our top tier conference in NLP. Actually, almost all of the top conferences in NLP are under ACL organization. So tutorials you get at these conferences are super high quality. And here you have slides and recordings for the whole tutorial on retrieval augmented generation. I've taken this slide to just show you that although we learned one classical information retrieval approach, BM25, and we have learned dense passage retrieval, and we have also learned about Colbert, there is many more, and it's an active area of research. So here, there are a bunch of other ways to retrieve documents that differ along what do we retrieve, how do we use the retrieval, when to retrieve, and so on, that researchers have been developing. So I want you to remember after this course that the retrieval systems I taught you are your necessary baselines, right? So whenever you start to build, someone hires you to build a retrieval system, you're always going to construct BM25, dense retrieval, maybe Colbert as your simple baselines, right? And your goal should then be to improve over those baselines if you deem you can, okay? So yeah, remember there is way more retrieval approaches than we have covered. Okay, so now we learned how to retrieve documents, but remember I'm not bringing that same visualization, I think, again. We now need to, based on the retrieved documents, answer the question, right? But the answer is should be somewhere in those documents. So we are going to learn 2 ways to answer based on the retrieved documents. One of them will be to extract the answer from the documents. That means predict the starting and ending position. And the other way we are going to approach this answering component is through text generation, our next token prediction, which we all know very well by now. And then we're going to, when we go into how to both retrieve and generate the answer, we are going to talk about some options for training. We're going to overview them. We won't go into nitty-gritty details, but we are going to go over 4 different options. Okay, before we go into answer extraction, are there any questions about the retrieval part?
What was the last word you said? You started with C.
So
You said the 3 basic options you said were PM25, dense retrieval, and
dense retrieval, we learned 2 approaches. One is DPR, dense passage retrieval, and the other one is Colmer. Yeah, so if that's not familiar, check the last lecture and you have a whole slide on it. Okay, let's get into then answer instruction. Oh no, I have leftover here. Well, it's so ugly, I will put everything here. And let's use whiteboard for this part actually. So I'm going to actually go here and then we are going to use slides again. Okay, so we are going to talk about how can we answer a given question given now available retrieve document. And for the simplicity, we are going to talk as if there is one, but if there is more than one, we just concatenate them into one long sequence. Okay, so answer extraction is what we are talking about. Okay, so first thing, our input to our model is going to be a string that is constructed by concatenating our query and our relevant document or more of them. So we're going to start again here, traditional approaches are again encoder only, transformer, MLM, pre-trained like BERT. So very often here we are going to have that special CLS token. I want to emphasize that you still can use decoder only models, right? And maybe just the CLS token, instead of CLS token, you would use, you don't necessarily need to use anything, but if anything, you will maybe emphasize that this is query, and you're going to start with query column, for example. So if you are using models like Llama or Qwen, we would, instead of using CLS, we would start with query column, and then we put our question or query tokens. All right, I won't repeat now here. This is just an alternative. Okay, maybe I will. And then you will separate your query or question tokens from your passage tokens. So with encoder only BERT-like models, you would use the special separator token. With something like Llama, you would maybe write passage column. So these newer versions of LLMs, they're thinking more, you use more natural sounding ways to delineate parts of text. And then you have passage tokens or document tokens. I keep switching from passage to document because in earlier version of this, we would use passages rather than long documents. These days, it doesn't really matter. So that's why I'm kind of going back and forth between passage and document. And here as well. Again, this can be 1 or 2, or, you know, it can be a string that you produce from 1 or more relevant documents. I'm going to emphasize model input. I will say here like BERT, and here like Llama 3 or whatever, Qwen 3. So these are decoder only transformers. Okay, now this is an important part. With answer extraction, we have this as an input, right? And we want to predict at which position our we have a start of our answer span, and at which position we have the end of our starting span. So honestly, I don't remember the exact detail. You can allow that the model predicts any of these as a starting and ending indices. Obviously, these question ones should not be, because this is not where the answer is, right? And your model will likely learn, but here for illustrations, I'm going to start here. So basically, our model goes over these passage or document tokens, and it's predicting whether this is an start or an end. Of course, it shouldn't predict that the end starts before the start. But again, this is something the model will learn from the data, and you don't need to do anything special about it. So it goes from over every position, and it's predicting what is the probability of this token being the starting token of my span, and what is the probability of this token being the ending of my answer span. And we are going to do that for every one of these token positions, right? Imagine I've done that. Imagine I have calculated the probability that this is a start or end at every token position. How can I use this information to predict what is the answer span? How can I choose one span as a one that I present? Yes.
Your span is going to start at the passage token that has the highest probability of being a start token, and it'll go to the token that has the highest probability of being the end token.
Yeah, right. So I have this probability, so I just choose this is going to be starting point of my answer, and this is going to be the ending point of my answer, and I just use the highest probability positions for those decisions. Okay, so we kind of get now how we are going to approach this, and the question then becomes, how do we calculate these probabilities, right? Now, I think for you, knowing what we know from this course, maybe you would say, well, we just make a linear transformation into some value that decides the probability, right? Like has been our classical approach. We define some new weight matrix, and this weight matrix gives us the probability, right? Here, I don't remember exactly why this is approached like this, but we are going to define two vectors. We are going to call them S for start and N for and E for end. So start and end tokens are going to be D-dimensional, where D is the dimension of our hidden representations of our model, right? So at the final layer of our BERT model, we get representation of every token, and whatever the size of that representation is, that's what D here is. Okay, so it's going to be same size of our token representations. They're going to be initially, I believe, randomly initialized. So we are going to use our Xavier-Glodot initialization here to just set some values. And these are going to be also parts of our weights, right? Also weights. We are going to change this value such that we get a better prediction of what is the most likely start and ending position here. Okay, so now for every token position, we have the final representation. So this is the final representation of token PJ. So we know that we pass our tokens starting from token embedding to BERT, and what we get in the end are highly contextualized nonlinear representations for each token. The way I'm going to define the probability of the starting position being position I is going to be defined through the dot product of this starting vector with this final representation of the ith token. So again, this is the same old idea we keep seeing in this course. So we have a vector product, dot product between starting vector and the ith token's final representation. And the higher this dot product is, generally we deem these two vectors to be more similar, or very often in this course, we kind of conflate that with the notion of importance, right? Similarity, importance, very often kind of synonyms in this course, although they shouldn't be. And then we know if I construct a softmax vector, I take softmax of the vector where I place dot product between S and every position P1 prime to Pm, I believe we have them, right? Prime. So this is m-dimensional vector, right? Here I have constructed, I just place these dot products in a vector, right? And I apply softmax, so that's going to give me a vector of which size? M size, right? Always the same. We're just going to squash these values between 0 and 1. And now I'm going to write this in a very mathy way and take ith position of this softmax value, right? So here, sorry guys, I know this is not what you can see super well, but I'll leave this here. So just to go over it, I have constructed m-dimensional vector consisting of m dot products between the starting vector and the token representations. I have applied softmax, which will squash each one of these values. And we know if this dot product is very, very large, we know that the ith value in this softmax vector is going to go towards what? 1, right? I don't know whether that was, I want to say something or 1, but I interpreted it as you're saying 1, right? So this is the first time we have seen this idea was when we, very first lecture, right? When I introduced sigmoid, I said, oh, the very high dot product between the weights vectors and the, feature vector, the higher it is, the sigmoid is going to be closer to 1, which is our notion of probability, right? So similarly here, very high product here will result with the probability for that ith element being very close to 1. If this was very close to very, very low, minus infinity, what would I get here?
Gets to 0.
Gets to 0, right? Okay.
That our probability of start BAI is the soft.
Exactly. Yeah. So we are going to then define our probability of start token being ith token as the ith value in this softmax vector. Now I'm going to write our softmax again, which is always seemingly a scary looking equation if you don't know this part, right? So Pi and sum of overall E to SPJ prime. Okay, let me make this a little bit more separated a little bit. Okay, so it's really important for me. Now we are going a little bit, faster into what is what, but you should know that what I have written here is the ith element in this softmax vector, right? And because softmax vector was produced out of these values, these dot products, this is why we have here as these same dot products. Okay, so this is going to be our probability that we have ith token as the starting token. Now, you will give me an equation for the, what is the probability that end is at the position, let's use K just to kind of avoid I there. So what is this equation going to be? Yeah,
The same thing, but instead of S, it's just E.
E, exactly, right? So we are going to basically repeat this process. We are going to use our ending vector, E, and we are going to say if the dot product between the ending vector and my current token's representation is really high, the probability of that token being this ending position should be really high, and the highest possible is 1. So I'm going to use the, now because I said K, it's going to be the kth value in our softmax vector. So E to S, oh, sorry, I immediately made a mistake. Okay, so dot product between E, B, K prime. And here we have again the same denominator, just using E in place of, nope. Okay. Yes.
So what exactly is this final representation of a passage token?
Uh-huh.
Yeah, what is this P prime in
Yeah.
comparison to just those regular passage tokens that we have?
Okay, I'm gonna challenge you a little bit to answer your own question. So imagine I use birth representation, right? Well, what do you think the final representation is? Make a guess. So let's start here. I have this input. I placed this input here, right? I put it inside to birth.
Okay.
When I say final representation of a given token, what's your guess of what's that? What is that?
Is it the final outputs from the last layer of the transformer?
Yeah, and what is final? It's a little bit, I would say, subjective, because there is always that output layer. But you're right, it's a final layer that produces token representations, right?
Okay.
So remember, when I shared that notebook, I invited you to think about every single transformer as a two modules, right? The one which makes token representations and the one which makes some predictions, be it next token predictions or classification predictions and or so on, which we refer to like a head, right? So you're right, like we put this into birth, and our representation part of birth at some point will have the final chance to contextualize and non-linearize token representation. So each one of these will have a new token embedded, right? And then this is our module that I will call representation module. And then after this, we have a head that can, if it's a classification head, in a decoder-only model, it's going to take the last token and classify it into a certain number of classes. If it's a language modeling head, it's going to predict next token. If this is an encoder-only model, we are going to take the CLS representation, again, either classify it or do whatever. So you're right, the final representation here is the representation of each one of these tokens after the final round of our, contextualizing, non-linearizing. Yeah.
Okay.
Okay, so now we have defined the probabilities. That's great, but we actually need the loss, right? And as we know, loss is going to be defined through these probabilities, right? So if I tell you we are going to use negative log likelihood, I want some of you to tell me what do we want to minimize? So we are going to minimize some negative log and then probability, right? Probability of what do we want to minimize here? I invite you to think about this most common way of talking about the LLM and then what we want to achieve here. Maybe you jump.
Well, so we're actually trying to minimize this problem, sorry, minimizing the problem.
Yeah, that's right.
So we're trying to maximize the probability that we chose the right start token.
That's right. So we want to maximize the probability which is the same way of saying to minimize negative log probabilities of two things. We want to have our starting position be what is truly starting position, and I'm going to call it I star, right? And we want our ending position to be the truly, the true ending position, what I'm going to call J star. Now, that's great, but I have defined not the joint probability, rather probability of something being the start and probability of something being the end. Which assumption can we use here to come into a situation we like? Yes, right. I knew you know. IID, right? So we assume that where I predict the starting position and where I predict the ending positions are two independent events. Do we generally agree with that? Yeah? How about the situation like me trying to predict ending before starting, right? Like they are somewhat dependent, right? I know that the ending should come after starting, and this is a great example where IID, we use it because we otherwise don't know what to do, but it's not, it's not really true. So we use it. YOLO, we go further. Negative log probability. Now these are two independent events, we say, so this becomes product of these independent probabilities. So we have probability of starting is I star times probability of end being this J star. Okay, and these I have just defined the equations for, which is great. I did change the symbol, so maybe let me return to the previous probability sign, especially because we have P there referring to. Okay, and because we have the here the logarithm of a product, we are going to just write it as a sum of logarithms, but because we have the negative sign here, it's going to be negative. So negative log probability of start minus negative log probability of ending. Let me just plug in our equations here. Just watch out, and I think this is a common mistake when we look into negative log likelihood training. So here we are talking about specific I star and specific J star. So here when you calculate probabilities, it needs to be for those positions, right? So here my I becomes whatever is I star, let's say it's 2, and here my K is J star. So I take the part of the softmax that's associated with those I star and J star. Yeah.
So this portion is almost like an extra fine tuning stage, I guess, where you have a bunch of queries and documents.
Yeah.
And you can annotated within this document or answers here.
Yeah.
Okay.
Yeah, exactly. So I said last time that we are going to kind of look into applications of that pre-training fine-tuning paradigm, and although later we are going to talk about instruction fine-tuning and prompting, and we might not do fine-tuning anymore, we are still in this class talking about these particular situations where we do have training data. So that's why we define the loss, right? Yeah.
What if you have a class that just like that?
Oh, that's a great question. We are going to talk about that in a second. Okay, so let me just, before we go into that, define my loss. Just don't forget, like, okay, this is how we define the loss. And as we just mentioned, we do have our training data, right? So our training data will consist of these queries, and we won't have the relevant passage, we retrieve it, but we will have I star and actually, sorry, that's wrong. We need to have retrieve passages, otherwise we wouldn't know what is the starting and ending position. So here we have the correct passage, and we have the position I star and J star for our answers. And we have I such, let me use K here. We have let's say, the, such examples. So here, K. So we use this, training data, we calculate the loss, and then we backpropagate. And, what we backpropagate through is, also important. We are going to change these guys. These are our weights, right? We are going to change their values. And we are going to change, the representation part of the phrasing. So weights that are here, right? We adjust those with the gradients.
So I guess for like a single query, right, we could have. Who knows how many documents, and within those documents, there could be. Like multiple points where there's a correct answer, are we,
Okay, we are now in this situation that I described, you assume there is only one span, yeah. Yeah, I can tell you more after about what to do otherwise, but yeah, here we assume only one correct answer, yeah. Okay, as I was saying, here are our weights and here are our weights. I've seen a few faces that were like, oh, what's happening? Is it clear where the weights are? I'm going to repeat it just to be sure we understand that. So we take a bird, let's say, and bird has, remember, it consists of encoder blocks, which have, transformations into query keys and values. Then we have turning multi-headed stuff into something shorter. Then we have weights of the free forward layers. All of those elements are our weights, right? So we are going to tune those. And also now we have introduced two new randomly initialized vectors. Oh, they're not here. S and E. Oh yeah, there. These two, and these are also our weights.
So we're updating both the transformer weights and these new weights that we've defined?
Yeah.
Okay.
Those are all of the weights. Yeah. Yeah, these we naturally need to change because they are random, they don't do anything smart at the beginning. And the transformer weights, you just want to learn better representations for your test. Okay, so now hopefully we know what the answer extraction part is. One thing I forgot to mention is, okay, we train this, we are done. How do we decide, like we calculate at the inference time probabilities? And we said we are going to take the highest probable span. Typically in practice, you would actually use this score, which is kind of the same, concept behind. Basically, you take, I think, just the products, SI, PI times, let me just check that I am not saying anything wrong. Yeah, so here, so for every, span that's determined by position I and J, you're going to calculate this score. And then you can rank all the spans in your input text, and you can return the highest scored one. I'll call this score. Is this clear? Yeah. It's not using this probabilistic notion here. And I don't know exactly why. It seems maybe unnecessary because whatever is high scoring here is going to be high scoring if you use the probability. So maybe it's just it doesn't. Yeah, this makes. Yeah.
we can go back real quick, and just, so we split, we have like two. Separate vectors, let's start and then they don't. Seem to communicate, also like in the picture too. And so. I'm not 100% sure why exactly we're back propagating through both of those back to the better weights.
So when you back propagate, you start with your loss, right? Where is it? I'm going to be so strong after this loss. Okay, here is my loss, right? So I get these values and then I need to kind of backtrack where did I get these values from, right? So I got this one from the product of S and the token representation. So you are going to backpropagate to, if you imagine these as two branches in a computational graph, you are going to backpropagate to the bottom of both of these branches. So you need to calculate derivative of the loss with respect to the S, but you also need to calculate the derivative of the loss with respect to the final representation. And final representation itself is a function of many, it's a composition, right? Composition function of many encoder blocks. So you need to backpropagate all to the input. Does this make sense?
Yeah, I think it's just the branch, like, I'm just imagining this like
Mhm.
weird thing. That it's just a little bit different than.
Yeah. I don't know. I mean, it does have these two, right? Kind of two products, and maybe that's a little bit confusing. To actually calculate the loss, it is a sum of two parts. And the way you can think about it, if it's easier, imagine how would you backpropagate if only this is your loss, only the start stuff is loss. And then imagine how would you backprop if it's only the ending stuff. It's basically this is what you're doing in a computational graph. You need to kind of change both of these because loss is a composition of these, right? And if you were to calculate gradients, this would become two independent in a sense of you can calculate gradient of this and sum it with the gradient of that, right? So in a way, you can also do everything independently and sum the changes. Yeah, it's a bit hard to show without the computational graph, but yeah, maybe later we can also kind of draw something over it. Yeah.
So architecture-wise, I know last time you mentioned how the retriever part of this question answering task is just some mathematical algorithm. There's no neural component to it. But now for this answer extraction part, because we're now dealing with weights that have parameters that, we update and whatnot, would that make that sort of, an additional neural component we're putting on top of this this transformer architecture?
You were in the lecture last time. Okay, so why do you think we have talked only about non-neural approaches about retrieval? What is this?
Dense retrieval is the one that is the neural approach.
Yeah, right.
Yeah.
So first of all, remember that we have a variety of retrieval approaches. One of them, you're right, was BM25, which is not neural and it's an option. But we also talked about neural ones, so don't forget about those.
Okay.
Yeah. So now you are right that you can think about this as a pipeline. You get using a neural or non-neural approach, whatever, you get some documents. And those documents then become the input to your answer extraction model. Yeah. However, we are going to talk about this when we go into these RAG systems. There is a question now about how to train this, right? Because you can train your retrieval completely independent of your answer extraction, right? And then at the inference time, although you're doing training, you always got your answer extractor, always got the actual relevant document and learn how to find the answer in the context of the relevant document. At the test time, full retrieval system, you will not have the human found relevant document here. Rather, this is going to be the output of your retrieval system. Okay. And now, the question is, isn't then training these independently a bad idea? Because they're actually a team, right? They actually at the end should function together. And yeah, that's one problem that we are facing when choosing this separate training approach, but separate training gives us other benefits. So when we turn into talking about how to train RAG system, the same benefits trade-off and benefits trade-offs apply to answer extraction being the thing that's in the answer rather than the generator that we are going to talk.
Okay.
But I'll come back to emphasizing this again. Yeah. So what you said is right in short, just don't forget that we have actually learned neural approaches to retrieval as well, in very short answer. Okay, there was already one good question about, let me return these for a moment. There was already a question about the length, and we'll come to that. But there is also another piece of information, which is what to do if we don't have an answer. And maybe you have noticed this, and maybe less these days, but in an earlier version of ChatGPT, right? And sometimes we are in such situation that simply our data store doesn't have the right information, and we should have a capacity that our model says there is no answer to this question. That's better than trying to give something and then fool people with misinformation. So the way people have approached this is to decide to have in the training data some instances where there is no answer, and then the starting ending position is chosen to be that of the CLS token. So basically, you are training a model to predict the CLS token's position when there is no answer. And then at the test time, if that turns out to be the predicted position, you can have just one additional if statement that says, oh, if CLS token was predicted, I will output, I don't know, or something along those lines. So just a little hack to consider this situation. But then you mentioned something that's incredibly important and has been, today we are trying to maximize what can be part of the input, but BERT-based approaches were very limited in what you can put in the input. The maximum length was only 512 tokens. So this question of what if our passages are longer than the maximum input length that my BERT-based model can take, what should I do then? Was a huge question in 2019, 2020. And what you could do is, I should have asked you this. You will probably, some of you will give me this as idea, but basically you can choose a window of a certain size. Very common choice was 128, and you can slide it through your input. So, no. Where is it? I'm trying to find where is the. Oh, there it is. Okay. I'm not going insane, I promise. This is I wanted to have this thing, and I want you to imagine this is a 512 tokens, right? So I actually, let's make it larger. Let's make it 2032, right? And the maximum number of tokens I can give to my BERT-based model is 512. What to do then? This is what we are talking about. And what I was starting to say is you choose the window of a certain size, such as 128. So imagine this is here 128. And then I just slide it by some stride, right? Let's say the stride is only one. I would move this 128 token window by one, right? Okay, so you can do that. You slide it, and then you get a bunch of these. I don't know why I wrote, and I'll immediately remove this. I had two different values, which bothered me. When you do that, you get a bunch of these pseudo passages, right? So I don't know, I don't want to do math here, but you can imagine if I'm striding a window of 128 to kind of go over to 2032 tokens, how many of such pseudo passages I would have. What you do is you pretend to do the same task of answer extraction in the context of these pseudo passages independently. So you're trying to predict the starting and ending position in the context of each one of them. And this is where these questions with no answer also becomes important, because then most of these, all except one, should have no answer as the answer. And only one of them should have the actual answer, where we do predict the starting and ending position. You can already imagine how pre-processing gets a little bit trickier here as well, because now what is the starting and ending in pseudo passage? What is that globally? You need to kind of keep that mapping as well. Okay, and then I changes. At the inference time, you're going to run the model on all pseudo passages, and you're going to calculate all those scores here. We have them in the context of each pseudo passage. And again, you're going to retrieve the highest scoring one as you were before, just not in the like from one passage, but from all of these pseudo passages. Okay, another issue that can happen when you start creating these pseudo passages is that sometimes you have what is the, you have created a window of tokens where the answer is now split between two of these, and that becomes finicky. So because your stride won't be massive, you will have a window where the answer is fully contained. During training, you're going to keep only that passage and discard these weird ones where the answer is split, to kind of not confuse the model, to kind of predict half of the answer. However, at the test time, you don't really have options, so because you need to pretend you don't know what the answer is, so you will need to keep all of these pseudo passages. So yeah, basically, when we deal with documents that are longer than the maximum input length, we have to deal with, trying to get all of the context. And this, slicing isn't ideal because you do forget, if you treat everything independently, you forget information from the beginning or the end of the passage. Now, if you, today, okay, I will come to the evaluation, but I do want to, okay, I'm going to talk about this. I don't know why I placed it so late, but I do want to talk about this part now. So we started with, BERT-based models had an input length of 512, but it became very soon very clear that we need larger input context, right? And at some point, it almost became like a currency. Like if there was a new LLM, everyone would emphasize what its input, or we say context length, is. Now, I want to mention why does length matter? Because I'm trying to visualize this for you. Like why are we restricted with the input length, right? If we are having decoder only model, and at the inference time, we are anyway creating new representations on flash. So there are two different components to why input length matters. So I'm going to say one, then other, then we are going to combine. The first thing that we need to know is that attention matrix is squared in the input length size, right? We have, remember that we have, by doing the query key multiplication, we have created an attention matrix, and that the shape of this matrix is input length by input length. And this is a problem because if we have really huge input, this becomes really, really huge, right? And it becomes problem because we need memory to store all the values in these matrices. But our memory sizes are bounded, right? Like we don't have infinite GPU memory. So if you are working for a pre-training team in Meta, let's say, you are given some computational budget and you use, okay, chinchilla laws to decide, oh, I want this size for this many tokens, right? And this is where you also kind of start to think about, well, if I'm going to use a standard representation of attention, this is how much I can fit in terms of the input length, right? Like you can't fit any size as the input. So your GPU memory and computational budget you have demands dictates what the input length could be. Other thing is also that ROPE, as we know, is the current choice for the encoding of positional information. And although in theory it should work for sequence lengths, we haven't seen. There is nothing in the theory of it that prevents it from encoding positions it hasn't seen during training well. But people have observed in practice is that the performance of language models deteriorates when we have sequences that are longer than we have seen during training. And this has been traced back to positional encoding. So positional encoding is affected by what it has seen during training. And during training, we can't have something arbitrarily large because we don't have enough GPU memory. Because of this, you should not expect that your LLM works for sequences that are longer than what the creators of the LLM have reported as the longest sequence they have encountered. And they will say our context length is blah, blah, blah. Yeah.
So is this kind of related to like the idea behind throwing an entire code base from some company at the cloud, let's say, and it not being able to perform well on such a large code base?
Could be, yeah. Yeah, if I don't know what's the code base in question and how long it is, because the lengths we can encode these days are pretty massive. So this plot here is kind of finished with 2024, but I don't think we have created LLMs that can process even longer lengths than these. So you can here see on the x-axis, we have model release date. On y-axis, we have input length, context length in number of tokens. You can see that BERT, earlier GPTs, T5, GPT-3, they are all here in 512 or at most 1,000 tokens. And you can see how quickly we're like, I need to be larger. That's really important. To the point that Gemini 1.5 Pro had 2 million tokens as a size. And this is a very funny way of thinking about how long these inputs are. So here, this is GPT 3.5 Turbo is here. So we have about 10,000 tokens. That's a fraction of the first Harry Potter book. And then you can see how many more books you can fit inside the input context length. These days, I think it's normal to see 200K. I don't think these millions of tokens are pretty usual. So, you know, as you mentioned, oh, this was a very long code base. Was it longer than 2 Harry Potter books? I mean, what is that code? Then it seems a little bit too long, right? So we can fit really long sequences in the current LLMs. And I don't know, I think this now is, okay, we can do this, but just being in this field for 10 years, the idea that you can fit the entire book into the input is crazy to me. And that you can do anything with this information and process it in some realistic time. So I think it's a really tremendous achievement just to be able to place all this information in the input. So yeah, I want to emphasize here, if you are tasked with working with a retrieval-based system where you retrieve some documents that become part of the input based on which you predict the answer, the number of documents you can place is actually pretty significant these days. And this might be a reason why you opt for using a little bit newer models rather than BERT-based models, because those you need to deal with these pseudo passages. Here you can put everything in the input, but then everything is going to be slower as well, because you still need to compute that gigantic attention metrics, right? So there are still benefit, trade-offs between, okay, do I want to deal with the shorter context length and create these pseudo passages, or do I want to shove everything in the input, call it a day, but then wait to actually have representations constructed? So there is definitely a trade-off between simplicity and the speed with which you can get to these representations. Related to the problem of input lengths, and what I kind of hint at when I said that construction of the input might be important, is that people have shown, the researchers have shown, that the models favor information that is at the beginning of the input you give them and at the end of the input. So there is this task called needle in a haystack, where you put some secret code into your input and you see how good the model performs at retrieving that hidden code, depending on where did you place this secret code. And here on this plot, you can see that the performance of this task deteriorates when this code is placed somewhere in the middle of this context. So although I said the ranking doesn't really matter, because we put everything in context, you might, knowing this information, decide, well, the first rank one will appear the first or the last, because I know this is where the model pays more attention. Okay, I'm going to come to the conflict between internal and parametric knowledge in a second. Okay, so we talk now at length about input lengths and what to do with that. I want to wrap our answer span extraction with how we evaluate it. So you will have two measurements here. One is called exact match. So you check whether you basically predict the same string that is in the goal data. So it's like an exact string match. And here for these two strings, the capital of France is Paris, Paris is the capital of France, you would get actually 0 as an exact match, because we are looking, maybe the way I have written it doesn't make it clear, but you are looking whether gold tokens match position-wise. So whether the is same as Paris, whether capital is same as is, and so on. So is this good? How do we feel about this metric? Rubbish, right? Like too strict. This is why often you will see token F1 score as a way to predict the as a answer span extraction evaluation. You will treat a gold and predicted as bag of words, and you are going to compute F1 over these two tokenized lists. So if these are my gold tokens, these are my predicted tokens, I will check how many of my predicted tokens appear in the list of gold tokens, and turns out all of them do. So the precision is 100%. And I will check how many of the gold tokens have I predicted. So how many of the gold tokens appear in the predicted tokens list? All of them do. So recall is 100% and F1 would be 100% too. So this is much, much better. But you will see both of these reported. Okay, we won't go over the notebook where we have this question answering answer extraction implemented, but here is the notebook that you have from Hugging Face. They have created this nice class called Auto Model for Question Answering. So if you use that class and if you use verb, it will create this S and E starting and ending vectors for you, and it will define a bunch of stuff that you don't need to then define. But I really encourage you, if you're interested in working with stuff like this ever in your life, to go over this notebook and especially look at how pre-processing becomes finicky. And we will see that the majority of this notebook is just making sure that pre-processing of the data and ensuring the starting and ending indices are where they should be is handled. So check this out if this interests you. I said that we don't have projects in this course because they tend to be not good with the size of the class, in my experience. So I don't ask you, there is no graded component of the course where I'll ask you, hey, fine tune a model like this and do something with it. I expect that if this is interesting to you, that if you want to do something like this in the future, that you will find some time to play around with these things. So again, not evaluating you on this because it's not important, rather it would be make the evaluation of this course just too complicated. Okay, so now we know how to do retrieval. We know how to do the answer extraction, but we also said that instead of extracting the answer, we can do conditional text generation, where conditioned on the retrieved document, we can, with the next token prediction, predict the answer by generating it. This is called retrieval augmented generation these days. Couple years back in 2020, we called this retriever generator architecture as opposed to retriever reader. So to emphasize that the part that gives us answer has changed. Instead of reading the answer from the input, we are generating the answer. Today, you might be even tempted to say, well, why do I need retrieval at all, right? Why can't I just generate the answer without retrieval component? And this is not a bad idea, but it might lead you to problems. So LLMs, we say, and I mentioned this already, during this large-scale pre-training, have acquired a lot of knowledge. And we call this knowledge parametric knowledge, but because it's encoded in the weights in some weird way. It's not like literally physically an input or output, rather it's somewhere in the weights. And although the model might use its parametric knowledge to answer the question correctly without having access to relevant information, very often in practice, we have seen the cases of so-called hallucination, which is a response that's not faithful to the facts of the world. Here is a taxonomy of hallucinations. So we have those that contradicts the evidence, what we know about the world, right? Or it is totally making up some new entity, like new person or organization, and so on. So we have seen a lot of these hallucinations. And when I talk to people at the School of Medicine, they will say, even small fraction of such hallucinations make it for them a huge problem, and they can't use certain LLM applications as long as hallucinations are the problem. This adding the retrieved documents to the input makes hallucination problem a little less problematic, because now instead of relying solely on its parametric knowledge, the model actually has some input text. It's conditioned on some information, and it is actually paying attention to that information. So retrieval augmented generation, although it sounds fancy, and although it might seem like something crazy new, it consists of components you actually know. It consists of the retrieval component, whatever you choose. It can be BM25, it can be dense retrieval, either DPR or Colbert used, or something even fancier. This component will give us some relevant documents. Then we're going to take those relevant documents, place it in the input together with our question, and we are going to give it to LLM to generate an answer using the next token prediction. And this is something you know very well by now, right? Like when we have gone through how do decoder-only based transformer models condition on text, we have went into a lot of details of that. This is basically what you do. It's just that conditioning part is really long now, where before it was maybe shorter. Remember when I talked about machine translation, source sequence was usually a single sentence. Okay, and now you can have retrieval augmented generation. You can either fine-tune it to generate these answers, or you tuned your retrieval, and if your LLM is already good at answering stuff in the context of what's in the input, if the pre-training was really, really good, you can reuse the language model it had, so maybe you're already fine like that. So sometimes you don't need to fine-tune the answer generation part. Okay, we talked about this. Now, let's talk about training. So we have this retrieval part and we have the answer extraction generation part. We can treat them as an independent, right? And during training, we can train retrieval to retrieve. And during training of answer generation, we can train it by giving the actual relevant documents. And we ask it to generate the answer or extract. So that would be independent training. These two things are, we train them independently. And then at the test time, we have the system of these two components where we use the retrieval to get the relevant documents. We put them as an input to the answer generation or extraction, right? So at the end, they work together, but during training, they have never worked together. The reason why we end up doing that is because otherwise, another option would be to do joint training, right? Where we have all of the documents in the data store. We want to check what is the probability of a document given the query. And we want to, of that particular document. And then if I choose that document to condition my answer generation on, what would be the probability of the right answer, right? And we do that for every single document in the data store. I could have asked you why this is a problematic, but given that this is so prominent here, I guess the question is silly. Obviously, the issue here is that our data store will have millions or billions of documents. So going over all of these for just a single query becomes terribly slow. This is just too much computation for getting loss for a single query. Too much is going to be too slow. So because it's too slow, maybe to make it a little just more concrete, we are iterating here, right, over all of these. So computing the loss is expensive, but the more expensive part is, of course, we need to calculate the gradient with respect to every one of single of these document representations. So we need to back propagate through our, let's say, BERT or GPT or whatever we have chosen for a single query as many times as there are documents, millions and billions, right? So if I had millions and billions queries, I need to have a lot of backward passes, and you can imagine how much memory and time that would consume. So it's simply too slow and too expensive. I neither have time nor memory to do this. So doing this jointly becomes really hard, and treating these training things independently is a feasible way to construct this system. However, it's a dissatisfactory because, as I said, during training, my answer generator will always see these relevant documents. And suddenly, the test time, these documents might not be so relevant, right? Like my retrieval system might not be so amazing. So now my answer generator had never learned to work in the presence of some noise. And this is not great, right? So I would like this to be at least a little bit more connected during training, such that they are better during the test time when they will definitely work together. So there are ways people try to achieve that. One simpler change people are doing to make things at least slightly better is to train the answer generator in the context not of human relevant annotated documents. So we don't give it document that the person has said this is the relevant document. Rather, we take whatever is the output of the retrieval component as an input to the answer generator, and we train the answer generator while keeping the retrieval frozen, meaning we don't change its weights, because that would be, as I said, expensive. So you do that, and then after you do that, you're like, all right, I'm gonna now change the retriever a little bit. So now you are changing the retriever based on the generated answer. Although I don't remember how exactly we do that because okay. So again, retrieval gives us some documents and answer generator generates answer based on it. So we have some loss from whether the answer was good or not. And we use it as we would say distance supervision to the retriever, right? We say, well, you gave me these documents, but I couldn't really answer the question really well with it. So how about you change your parameters such that we can answer the question correctly, right? So this is a case of distance supervision where you are not using the training signal of the retriever to change its parameters. Rather, you use the distance supervision, the answer quality that's based on the retriever part. But this is still not exactly joint. And there are still attempts to do joint training. So there are two options people are using. One of them is works by making the updates every once in a blue moon, right? So you decide that at some point the index, meaning our data structure where we store the data store vectors, is now too stale, and you simply decide to wait a long time with whatever compute you have to update these representations. So update the retriever weights and reproduce new vectors for every single document in a data store. Something a little bit more practical is to use the so-called in-batch approximation. So for here, you are going to take some batch of documents, and you are going to have, for sure, have the document that's truly relevant to your query, and then some other ones that are not relevant. So here in this visualization, we have chosen 10,000 documents from our data store, and one of them is going to be relevant, others are not. And we decide to pretend this is our data store right now, and we are going to change vectors of documents that we have chosen to be part of the batch and not others. And here I want to just emphasize how the losses look like. We are going to turn the joint loss into sum of two losses, the loss for the retriever and loss for the generator. The loss for the retriever will be what we have seen in the last lecture. It's going to be negative log probability of giving a label being relevant to the document that's actually relevant, right? So that's the value in our softmax vector, softmax that produced by adding these dot products right here. I call them similarities between the query and the query's representation and representation of the relevant document. So nothing has changed here relative to what we have seen in the last lecture. Here, for the generator loss, we are going to use our basically next token prediction loss, right? So we know what is the next token. Here, I'm writing it as I correct, but this is going to be multiple tokens, right? So here you can imagine it's a sum of individual probabilities for each and correct answer token. But here, what is important is that this document is sampled based on the retriever, right? So here, I mean, it's a fancy way to say, give me the most relevant document, right? Like I have this probability and whatever is the highest one, I'm going to choose as the relevant document, and that becomes the input here. Okay, so there is an interplay between these two losses. And sometimes you will also have some special terms in front of the retriever or generator to kind of say what is more important to tune here. So to recap, with the retrieval augmented generation, we have the retrieval and we have the answer generation component. It is the same issue for the architecture when instead of answer generation, we have answer extraction. The question becomes how to train these. And the most simple thing to do is to treat them independently during training, retriever and generator or answer extractor, and that's it. But this comes we are penalized by performance, basically. What we are going to see is that system is going to work worse than if we don't treat this as separate, but rather as joint, because they actually are. The problem with joint training is that it's more computationally expensive and complicated. So it really depends on the applications and how bad are the results you get from the simple approach. Maybe with simple approach, you get something strong and you're like, not worth to go into that whole joint training business. Sometimes your employer will say, I simply need the best performance, and you want to show them you tried all the options. If you want to see some more concrete results, check the section 5 in this tutorial. But we are going to stop here, and then next week we are going to jump into summarization and how to evaluate text generation. And we are also going to have our practicum. If you haven't started the work on your assignment, do it right away. I don't know how the experience is so far, but from the previous time I was teaching this course, this assignment was a bit more involved than the previous ones. Okay, good luck with that. See you next week.